Thank you for the introduction and for inviting me to give this talk and to talk a little bit about my work. I'm going to talk about non-speculative reordering of memory operations while having a strong consistency. I will move a little bit more to the hardware side. The previous two talks were focusing on the software part. And I'm going to start with explanation about program order and memory consistency, and then how processors for multicores relax this memory order with a store buffer, how can also keep the memory order of some other operations with speculation, and our non-speculative solution. And finally, I will present some results and the conclusions. So first, about program order. We have here a code, the example of a code where there is one thread, is reading the value of a variable, global variable x in a register 0, then another variable y in the register 1. And the question here is, what happens if the core, the cache memory, reorder these two operations? So in a single thread or in a single core, nothing happens. It's possible because there is no data dependencies between them. But we are in the multicore day. So if we go to multicores and we run two threads, and this second thread will go and execute a write on y and a write on x, this can have a result that is not the one expected by the programmer. So reordering is not the intuition that the programmer has. And I'm going to have this code with example without reordering the code and reordering it. So I label this code, the load x, lx, load y, ly, and the store with s. And there are 6 possibles interleaving for this code that can happen at runtime when you execute concurrently thread 1 and thread 2. First, interleaving, for example, is that the two loads happen first. Then the value is going to be 0, 0, 0 for the y, 0 for the x. In the other corner, we have first the stores. So the results that we will get when we load to the registers will be 1 and 1. In the other 4 cases of interleavings, x will store before after loads, so x will be 0 and y will be 1. So if we keep the order of the operations, it's impossible to get with this code 0, 1, 0. But if we reorder the two loads, in one of the scenarios out of the 6 interleavings, we can find that we can get this 1, 0. And it's exactly where the two stores comes in between the two loads. And the same results can be obtained if we reorder the two stores instead of the two loads. So the programmer's intuition will be that we keep this program order. And for that, we define the memory consistency model to define the behavior of a load operation and a store. So if I want that a load that is in program order, PO here, I program it and I put in the code before the second load, I say this rule, which is load. I do not allow reorderings in the loads. I can do the same with a load and a store, and with all the 4 possible combinations between load and stores. So these are the consistency rules. Like if we keep them, we will have the better intuition from the programmer point of view. But if we break them, we maybe playing with the intuition of the programmer. So we have here the problem that we want to guarantee correctness. We want that the programmer writes a code that the output is the one that it expects, but also the cores, the multicores, the processor want to reorder some operations in order to be faster. So we cannot wait for a memory operation to finish in order to execute the next one. The multicores will execute them in parallel. And by executing in parallel, the memory system can satisfy one operations before other, and therefore they may be reordered. So this is a problem that is particular for the multicores, not from the single cores. And the industry has proposed two solutions for that to get the performance. One is the store buffer, and the second is speculation. I'm going to start with the store buffer. So all the multicores have a store buffer. And the reason is that the store operation usually requires to be performed to have in the cache memory the unique copy of that cache line. And for that, sometimes we'll need to call the cache coherence protocol, and we'll send some invalidations to the other caches to get the exclusivity to write it. This is a long latency operation, and therefore the multicores have a store buffer to put the stores in a side place and allow the other operation to execute. How this store buffer works? So we have here a program that is going to execute store first and a load next. And we have our reorder buffer or our pipeline. Here is the head, and we have our store buffer. And we have memory here that can be the cache, the first level cache, second main memory, written as a single memory piece. So when the store and the loads go into the pipeline in order, and we execute the store, what the processor does is to put the store in the store buffer, holding there, waiting for the permission to come. Then the load can execute, take the data from memory, and finally the store will write into memory. What we are doing here is that we are effectively reordering the load and the store. So the store buffer breaks the store load rule. This is not very intuitive to the programmer, but according to Intel or AMD, is intuitively enough. So it's only a few algorithms, the ones that are not going to behave as expected. Most of the code is going to behave as expected by the programmer. And therefore, Intel and AMD provide this consistency model that is the total store order. This order will respect the order 3 rules: load to load, load to store, and store to store. Will not enforce the store to load, and with this, they are doing a claim that is more important, the performance, most of the time, that the programmer intuition, if it's not too big the deal that they do to the programmer. So what are the consequences of having the store buffer? Well, the first one is that we relax the store to load order. The second one is that the load to store order is not important anymore, because we are going to be able to delay the stores as much as we want, and it will be hard the chances that the store can execute before the load. There is no need to try to execute a store before a load. The store and store reordering gets a little bit less important because we have this buffer where we are placing all the stores. Even this store have to be in order, is not so critical because we have a buffer with some time that we can save there. We have been doing some research in this line to reorder writes from the L1 cache to the last level cache. But in this talk, I'm going to focus in the load problem, which is the bottleneck now that we have relaxed the stores thanks to the reorder buffer. So the second technique that the multicores employ is speculation. And the key here is to being able to execute the load operation out of order at the same time that we guarantee the load-to-load order. So we have here an example, and I'm going to show how the two loads or a bunch of loads can be reordered even if they are issued in order. So we have the first load. This is the load queue, the load where all the queue where all the loads go in order, and the first one miss in the L1 cache. The second one then, the first one hit in the L1 cache. The second one no miss in the L1 cache. And then I have to wait for the data, but we can issue the other ones. Some of them will miss, some other will hit. And the end result is that the load 2 and the load 5 are going to be resolved after the other ones. So effectively reordering them. So if we reorder these loads, as we saw in the first slide, this can affect the programmer intuition. But does it happen always? So the answer is no, it's not always. You have the same code. We know that for this code we cannot see 1 and 0. And if, for example, the two loads happen first, we will see 0, 0. Even if these two loads have been reordered with respect to the original code, we will see that the value is 0, 0. But if we have the example where the two stores go in between the two loads, then we can see the incorrect. So we can allow to reorder these loads if they are not seen by other stores. So this is the key thing in the multicores to allow a speculative load-to-load reordering. So I will start with some definition to understand better this problem. So a load is going to be considered performed when takes the data from the cache and load it into the register. Then load will be speculatively with respect to the memory, when has been performed and there is an early younger load that has not been performed. And at that load, I'm going to call the source of the speculation. All the performed loads after it will be the speculative loads. So this load is the one that splits the load queue or all the loads in ordered loads, this one and the ones that are older than it, and not ordered loads, the ones that are younger than it. So how a processor can issue the load in parallel and also keeping this order. So I'm going to show the same example than before, two loads, not that the load Y gets reordered and with the load X, and the two stores are going to be executed in between them. So this will give the result that we don't want to see, but still we want to issue the two loads at the same time. So first, we will issue load X, which is the first one in program order, that will miss in the cache. This is the source of speculation. We have now a load that has not been resolved. And then this will go to find the data in the shared cache or in the main memory. Then we issue load Y that hit in the cache. That's why the load, the second load, gets reordered with respect to the first one. And now is the second core, the one that is going to do the write in Y, and goes and invalidates the data in Y that has been speculatively loaded. What processor do is to cancel this load, re-execute that load, and re-execute all the instructions that depend on that load. This is costly because the processor did some work that have to be redone again. But it's even worse because when we have evictions, when we have load some data that has to be evicted from the cache, we will not see anymore the invalidation from that load. If we cannot get the invalidation from that load, means that we cannot cancel this load. So we need to conservatively cancel this load when we evict the data from the cache. So if we have some data in our cache that has been loaded by a speculative load, and we evict that data, we cancel that load and all the instruction. Even if no other thread is going to access it, it's conservatively done. So even in single thread programs can have this cancel squash and re-execute of some loads. So our solution, well, the problems of this speculation is the following. Despite that this is the only solution that is implemented now in current multiprocessors, is good because this squashing is not frequent. Most of the times, you execute the load, it's speculatively until it stops being speculatively, and no squashes are going to be done. But this requires to hold resources in the reorder buffer, in the load queue. You cannot free these resources until the load is not committed, or until you are sure that the load is not going to be squashed or cancelled. So a question that we are asking ourselves in our research is how can we execute the loads out of order in a non-speculative way, and also giving this load and to load order, which is the intuition that the programmer will have. So here is our non-speculative solution that we call writer's block. And basically what we do is that we execute load simultaneously, keep finally the load to load order, and we don't rely on speculation. How do we do that? We block write requests, why we call it writer's block, and we do that with the help of the cache coherence protocol. Here there is an example of how we do it. So we have the same load queue, we have the same code, the same program. The first load is going to miss the cache. The second load is going to hit the cache. And now when the write is going to invalidate the second load, we tell to the write, stop. You cannot invalidate an M-speculative load. So with this, we force this store to be executed instead of here, or instead of before this load, to be executed after. Ideally, we just need to delay this store. I mean, the problem here is that the store that is before the X should be after. But stopping this store is harder than just stopping the previous store. And since we are going to have the stores in order, by stopping the first one, we will stop the second one. Until when do we need to stop? We will stop until y stops being speculative, which is when x will perform. So we wait here, and when x is resolved, the data goes to the cache, gets it. It's now green, means that it's performed. Now we can let this write to go on, and store x will execute after load x. Store y, and therefore store x. And what happened with the evictions? So with eviction, we have the problem that when we evict something, we are not going to see the invalidation, and we cannot stop it. So in this case, what we do is, first, we do silent evictions. Basically, what silent evictions are is, I'm not going to tell to the system that I don't have this copy anymore, such that if some other core wants to write, it will send me the invalidation. We have shown that the silent evictions are even more effective than the noise evictions. But we have the problem, what if the data that we have is dirty? We need to notify, or we need to write back this data. So what we do is, okay, we write back the data, but we say to the share cache, to the directory, the ones that keep the state of who shares its data, we tell him, if you get right, you need to invalidate, you need to notify us about that, such that we can stop it. But stopping writes is simple, is a very easy solution, but the problem is that can have deadlocks. So in the example that we had before, if we stop a write here, it may be the case that both the line X and the line Y belong to the same cache line. This is the kind of the example of the fault sharing that we were discussing in the previous talk. So these two variables map to the same cache line, and the directory is blocking the cache line because it's doing the invalidation for Y. When this permission for X comes, it will be blocked because it's in process. So we have a deadlock here. How do we solve that? So the solution is to allow all the loads to pass a store blocking in the shared memory or in the directory. By doing that, we resolve the deadlock, we can get the data, load X can be non-speculative, can be performed, and then we can resolve. And we don't have deadlock anymore here. But this can cause live lock. So we resolve one problem and create another one. And the reason is that if we allow the loads to bypass constantly, we are creating new copies in the cache. So we are, for example, in a block state, we read a new cache line, we unblock the previous one, but then we have to invalidate again the new line that we read. And by invalidating the new line that we read, it can be that we invalidate an M-speculative line, and this will block. So again, we go to the block state, and so on and so forth. We will be in a live block. Always a new processor asking for a line, and when we solve one deadlock, we will have other one, another. So the solution here is to give non-cacheable copies. So I'm going to, in these cases where I'm in a writer's block state and I'm letting the loads to go through, I'm going to give to the loads a non-cacheable data that will not require an invalidation, which also implies that if they are M-speculative, they cannot use it, because the rule here is that if you will ensure correctness with the invalidations, and you will not receive an invalidation for a non-cacheable block. So, in general, we delay writes, and by delaying writes, we can cause deadlock. So, the deadlock will never happen if we allow the loads always to succeed. And to allow the loads always to succeed, we need to play a little bit more tricks. And for example, we always have in the MSHR, in the register that have all the outstanding misses, we always will have a space for a load, even if it's a store for the same address there. If we have the last level cache full, we can always send a non-cacheable copy. And if we have atomic read modified and writes, we can also play them in order, because these are more complex. So, once we have these non-speculative loads, the advantage is that we can commit them out of order. So, by committing them out of order, we can release a lot of resources, such as the reorder buffer entry, the load queue entry. And out of order commit was proposed in 2004 by Bell and Lipasti, and states the conditions for safe out of order commit. And one of them is that you can commit if the load is not speculative. We make all the loads never to be speculative, and therefore we can remove them from the reorder buffer, from the load queue out of order. This will save more space and will reduce the bottleneck in the multicores that can be the reorder buffer or the load queue. So we performed some evaluation results with the GEMS simulator and our out-of-order processor model. We tested for 16 cores and 3 different configurations. A small reorder buffer, 32 entries, a normal size reorder buffer, or more moderate size, which is equivalent to the Nehalem processor, 128, and the Haswell, more high performance, 192 entries. We ran 2 benchmark suites, the S+3, that is a modification of the S+2 benchmark suite that fixed some bugs that were in the previous version, and the Parsec 3. And we ran both the traditional protocol that is implemented in our system and our protocol, writers block, with small extensions in this directory protocol, basically blocking the stores and avoiding the locks. We tried the 2 techniques, in order commit and out of order commit. So first, we are blocking writes, and the first question can be, okay, if we block writes, we are delaying this write, and we can delay the other core. What is the effect on that? Well, by the same reason that speculation works, that is, it's not probably to happen, the stores are not blocked frequently. So actually, well, as we increase in this graph, we are increasing we have the Silvermont, Nehalem, and Haswell, so 32, 128, and 192 entries in the reorder buffer. As we increase it, we see more writes that block. But still, in the worst case, is less than 5 writes blocks per 10,000 stores. The similar thing happened with the non-cacheable data. We are giving non-cacheable data when we are blocking the store, and non-cacheable data is not efficient because for every load that we have, we need to re-ask for it and we will miss in the L1 cache. But this is not happen frequently neither. We have one non-cacheable data per 100,000 loads. And when we compare the writers block protocol with a directory protocol, we thought including out of order commit yet is the two first bar there. We can see in this graph that show the stalls, the percentage of the stalls in time, that is exactly the same. So delaying the writes is not increasing the contention in the protocol. But when we apply the out-of-order commit, our advantages are more than if we have speculative loads. And the reason is that we reduce the contention in the reorder buffer, less store cycles because of the reorder buffer and because of the load queue. This finally translates into performance improvement, 111% with respect to a directory protocol when we have out-of-order commit, and similar result when the normalized line here, similar when we don't have the out-of-order commit. So to conclude, so with the help of the cache coherence protocol, it's possible, and also without harming performance, to convert speculative loads into non-speculative loads, being able to execute them in parallel and keeping the load-to-load order. And we can apply other techniques such as out-of-order commit and improve the execution times of the multicores. So thank you very much, and I will answer the questions.